Okay, let's go.
Alright, so I forgot to bring your midterm, so sorry about that, but all your grades are in, everything's up to date. It is what it is. So you should all know what your semester 1 grades are. And then hopefully I remember to bring all your stuff back next week so that you can go over the questions you had. But, so this semester, we're starting with probability. And I'll give you the warning that I always give with probability as we go through it. We're going to be developing a mathematical model called a sample space, which we will use to calculate probabilities. Now, the vast majority of the probability problems that we're going to solve in this chapter, you do not need to take the time to build a sample space for to do the math on. It's going to be intuitive to you, it's going to be obvious to you. You're going to want to not do that. Don't skip that step. The point of going over probabilities, the way that we're going to go over them in this chapter, isn't to get you to be able to calculate that the odds of rolling heads flipping heads 3 times in a row is 1/8. That's intuitive. I know that you guys don't need to build a sample space to figure out that the odds of me flipping heads 3 times in a row is 1/8. And so when you come across a problem that wants you to build a sample space to calculate that, you're going to want to skip straight to the answer and write 1/8. Because probability starts out really simple early on. Probability is one of those topics that gets really, really complex as you go down the line. And you're going to have to come back to using the mathematical model to calculate probabilities. So I'm going to introduce you to the mathematical model. You're going to want to be lazy. You're going to want to not use it. You're going to want to just solve the problems and not use the mathematical model. And then when we get to the hard problems, you're going to be in a lot of trouble. So the point is not, do you know how to calculate a simple probability? That is not the point. The point is, do you know how to capture it with the mathematical model? So that's my big warning. So it's going to feel like a lot of work for an easy problem. That's intentional. We're starting out intentionally with easy problems so that you can check with your own intuition. You know what the answer should be already. Did you build the model right? So the point is teaching you how to build a model. It's not about calculating the probability. Does that make sense? So as we do problems, if you just write out the probability and put a box around it, that gets you a big old no points. Maybe a point. That's not what we're after. We're after, can you build a model? Not can you calculate the probability. I know it feels like I'm stressing that a lot, but without fail, you guys are going to get lazy, not do it, later and get me in trouble. That's the way it goes. So, there's the warning. So let's go over what exactly a sample space is. And this is a cool chapter because this kind of gives you the sense of where science begins and math comes into application. So in science, what do? We look at real world phenomena and we try to come up with a mathematical model that captures that real world phenomena. And then we do math to make predictions, and then we check our predictions against the real world phenomena. Okay? And so this is a really simple way that you can see it in action. And so for doing probabilities, we're going to create something called a sample space. So what's a sample space? It's a mathematical model. It's a mathematical object. A sample space is an ordered pair SP, where S is a finite, non-empty set, and P is a function whose domain is S, and whose output is real numbers. It's the probability function. So, P is a function from the sample space to real numbers, where the probability of each individual outcome is always greater than or equal to 0. We don't have a concept of negative probabilities, is what that's saying. And the sum of the probabilities is 1. So we don't have a probability space where the probabilities add up to over 100%. Okay? So let's do an example, then we'll go over that definition one more time. Rolling a dice. So rolling a dice, we can create this. Remember, rolling a dice, that's a very physical phenomenon. That's not a mathematical phenomenon. It's a physical phenomenon. I roll a dice. It's something that happens out in the real world. We can create a sample space that would capture rolling a dice. So S, all the possible outcomes that we have, the set of outcomes would be 1, 2, 3, 4, 5, and 6. Right? And we say that the probability of each one of those events is what? 1/6. We say the probability of rolling a 1 is 1/6. The probability of rolling a 2 is 1/6. The probability of rolling a 3 is 1/6, etc. So my sample space is this ordered pair SP, where S is a set, 1 through 6, and P is this function which assigns 1/6 to each of these possible outcomes. Notice P is a probability function. It passes both requirements. 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 is 1. And none of these probabilities are negative. Right? We don't have a notion of there's a negative 2/3 chance of me rolling a 2. But notice I could have put 7 in here and said, oh, and the probability of 7, what's that? 0. And it still works. So this is the correct sample space for this scenario. It's, you have a scenario, create the sample space, however you want. It's completely up to you. Maybe your sample space captures useful information, maybe it doesn't. Does that make sense?
Okay.
Sample space is just a mathematical model that follows these properties. If it makes sense compared to what goes on in the real world, great. If it doesn't, it can still be a sample space. So this is still perfectly valid. Now, to help drive the point home that you have choice in how these things work, here's another sample space I created. What are all the possible outcomes? You can roll 1, a 2, a 3, a 4, a 5, a 6. And let's say this time, when I was playing in the real world, I found out it was a loaded die, and the 1 kept coming up a lot. So 1 has a probability of 1/2, and all the other ones have a probability of 1/10. Now, is this a sample space?
Yeah.
Are you sure?
Yeah.
Okay, good. Sample space, perfectly valid. These are two perfectly valid sample spaces for rolling a 6-sided die.
Even though there's a 7 and it's a 6-sided die.
Yeah. What was the probability of getting a 7? 0 is how we interpreted that. Now, we still could have done 0, 0, 0, 0, 0, 0, 0, and then a 1 there. Turns out it's completely useless information. Nobody captures what we were after, but it's still a sample space. So there is no, this is the right sample space. There is that sample space useful? Okay? And this could be a useful sample space if you're talking about a loaded die. This could be a useful sample space if you're talking about what's called a fair die. Now, I'm going to use that terminology, fair coin, fair die. That means exactly what you think it means. Each outcome is equally likely. Right? All right, let's look at another sample space. Let's say I come across this spinner out in the world. Right? And I want to create a sample space to capture the idea of the spinner. And pretend it didn't have the numbers on there. I might arbitrarily decide I'm going to call this area 1, this area 2, this area 3, this area 4, and try and create a sample space that makes probabilities on this seem useful, right? So I might say, okay, my sample space is, there's these 4 areas I can add up, 1, 2, 3, 4. The probability of that looks like it's about 1/2, that looks like it's about 1/4, and those two both look like they're about 1/8. So there's my sample space. Right? Maybe I go and measure a little bit better. I found this one's slightly bigger than this one. So, and it should have been whatever it should have been, but it's just a sample space that I created to try and capture the probabilities that I want to capture here. Good? Another one. Sample space for rolling a pair of dice. Now, rolling a pair of dice, you can get 1, 1, 1, 2, 1, 3, all the way down to 6, 5, 6, 6, right? So I said we could have the set of all possible outcomes be the Cartesian product of these two sets. You remember the Cartesian product? It's all the possible ordered pairs you can get where the first element comes from this set and the second element comes from this set. You with me?
Is that right?
Yes.
I didn't think S would be
Well, so it's going to be 1, 1, comma, 1, 2, comma, 1, 3, comma, all the way up to 6, 6. Right? That's how I'm going to represent my sample space. This represents the rule. The first dice was a 1 and the second die was a 2.
Oh.
That's how I'm choosing to interpret it. I could have just as easily done like pictures like this, right?
No, I know. I just, okay. That's not what I was, okay.
Okay. So how big is this set? How many elements are in this set? What?
There's a lot.
What did you say?
She said 36.
Why are you backing down from 36? It's 36. That's the answer.
This is the power of 2, right?
No, you don't get credit for that. You back down.
So smart, David.
We had 6 options for the first element and 6 options for the second element.
Right.
36. So hopefully that makes good sense. So the odds of a particular die rule are
1 in 36.
1 in 36. So the probability of a specific outcome is 1 in 36 for all outcomes in the outcomes, in the set of all possible outcomes. Good?
Okay, then.
Or P, here's one way that we could write P. Here's a more verbose way that we could write P.
Right.
P equals, what do we assign to 1, 1? 136. What do we assign to 1, 2? 136. What do we assign to 6, 6? 136.
Okay. Or you just write it like that?
This is how I would recommend writing it. This is a perfectly valid way to write it.
So-
Because that's a function still, okay?
That's supposed to, so that first notation is basically just saying, this is the probability of any outcome.
Remember, you're already used to this notation. You just need to retrain it. When I say f of x equals 10, what does that mean? That means for any x you plug in there, you get 10 out. P of s equals 136. I mean, I may get to the point where I stop writing that stuff. I'm going to say P of s equals 1 over 36. That means for any outcome you plug in there, the probability of it is 1 over 36.
No matter what you plug in.
No matter what you plug in, the same way that if you were to graph this, right, it's just a constant, right, 10.
Right.
Yeah. So you're used to this notation already. You're seeing it in different contexts.
Right.
Or you could write it out this way if you want, which is very tedious. But demonstrate to understand. Okay, let's do another one. A poker hand. You guys understand the general rules of how poker works?
Yeah.
You end up with 5 cards when it's all said and done, and you try to score as much as you can with those 5 cards. So, if we were calculating probabilities for the game of poker, we would have S be all possible sets of 5 cards that you could get, right?
Okay.
So, one of those might be ace of hearts, 2 of hearts, 3 of hearts, 4 of hearts, 5 of hearts, and obviously I'm not going to write out all the possible things. A ton, exactly. If you were to weigh it, it comes out to 2,000 pounds. How does he do that?
What?
That's okay.
Alright, what's important is the size of S. How big is S? It's 52 choose 5.
Oh, yeah.
It's the set of all possible